All right, we're still talking about screening tests, Chapter 11. We left off talking about reliability and validity, the different types of reliability and the different types of validity. But now we're going to talk a little bit about the interrelationship between reliability and validity. And I want you to think about it is possible for a measure to be highly reliable but invalid. So you can have a test that is precise. It's measuring exactly over and over the same type of measurement, but it might not be valid. It might not even be accurate. But it is impossible for a measure to be valid, or it is not possible for a measure to be valid but unreliable. And the way that you would look at this, I like to use the target, like an archery or a gun target, where you can have, for example, within target A, you can have a test that is reliable but invalid, as in it's not accurate, it's not within the bullseye. You can also have a test that is unreliable and invalid, as in it's not precise, as in you don't have a tight group of, or a tight screening test, but also it's not measuring what you're intending to measure, the disease outcome or the predisposition for a particular disease. And then last but not least is that you have a test that is reliable as well as valid. So it's not possible to have a test that is valid but unreliable. Okay? If you have questions about that, I'd be happy to talk more with you one-on-one. So when you think about some of these aspects, when we think about unreliability and whether a test is invalid, there's things that can contribute to that. And I will talk a few minutes about some of the sources that can make a test unreliable and invalid. For example, measurement bias, where you can have constant errors that are introduced by a faulty measuring device and that tend to reduce the reliability of measurement. So like a miscalibrated blood pressure manometer, the example that I gave before in the recorded lecture. And so it just is not measuring at all any type of precision. Then you can also have something that's called the halo effect bias that measures the validity in questionnaire, or that affects the validity of a questionnaire measurements. So one way to look at this is that a healthcare provider's tendency to rate a patient's sexual behavior use in a particular manner. So what I'm trying to get at, for example, is that you have a halo effect by, if you're going to go and give a survey to an individual, you make presumptions about a particular individual's potential behavior based on the way that they look or the way that they act. And so the example here that I'm giving is that if you have a healthcare provider, you have a patient that walks into a clinic, and that you then base general opinion about the patient's characteristics without even obtaining any specific information about past sexual behavior. And so, for example, if a patient walks in dressed a certain way, there is that potential where you can have bias that could be introduced, and that's called the halo effect. And then there's also another component that's called social desirability effect, and this is where the participant that's completing the surveillance tool will attempt to answer or respond in a way that they think is most agreeable to the social norms or to what the researcher or what the screening test evaluator would potentially want to hear. And that's where, for example, with this could be male and or female sexual frequency reports. There's been a lot of data to demonstrate that you can go into a high school or go into a college group, a tight-knit college group, and look at how many times have you had sex in the last year, and you record that among males and you record that among females, and you can see major differences, even though we know that they can have sex outside of that particular surveillance group. We know that if there is a major difference in that, in the data that's collected, we start to potentially think that there could be that social desirability effects, because that's what we want to be able, that's what we expect to hear, is that as a male, it's it's all about the number of conquests, whereas with females, we the presumed thinking is you don't want to, an individual doesn't want to be looked at in that way. And so that's where we get finally to another 2x2 table. Now, it's important when we talk about reliability and we talk about validity and we talk about that interrelationship, we're actually trying to determine, does this screening test actually measure what we intended to measure? How does this screening test, how does the data that comes out with this screening test match up to a gold standard that might be available or that needs to be available? Now, when you look at this 2x2 table, I want you to recognize and understand, even though we use the same type of table, the top part of the table is not based on disease. It's on the gold standard test to determine disease or to determine health behavior. Whereas the left side of the table, it's not based on exposure. This is what determining whether that particular screening test result is positive or negative. So we have a similar type of distribution, but we're now trying to determine, does the screening test actually measure, is it reliable and is it precise? And that's what we're trying to come to. And so that's where the measures of validity of a screening test, the type of calculations that we're going to determine, is it accurate, is that we're going to determine within validity sensitivity and specificity. Sensitivity is the ability of the test to identify correctly all screened individuals who actually have the disease. Whereas specificity is the ability of a test, a screening test, to identify only non-diseased individuals who actually do not have the disease. So you can see the calculations that would need to be done. With sensitivity, it's A over A plus C. So we go back to this particular test. So sensitivity is A, as in the screening test tells you that it's positive, and the gold standard also confirms that that individual also has that disease. So what we're seeing is how sensitive is this test, this screening test? So it's A divided by A plus C. Whereas with specificity, it's D divided by B plus D. So it's D, is it specific, divided by B plus D. And that's, I just went over that same calculation with this slide. So then we also want to measure predictive value positive as well as predictive value negative. And this is the proportion of individuals screened positive by the test. So this is the proportion of individuals that screen positive by the surveillance test who actually have the disease. This is A divided by A plus B. Whereas predictive value negative is the proportion of individuals who are screened negative with that screening test by the test who do not actually have the disease. So we're trying to determine, is this particular screening test valid? As in, is it sensitive? Is it specific? Do we have predictive value positive and do we have predictive value negative? So you can see here with this 2x2 table is that our predictive value positive is A, the screening test positive that actually do have the disease, divided by the screening test that says that they're all the ones that say they're positive. So it's not incidence. So when you look at this is how you would calculate incidence in the disease and the incidence in the non-disease, or the non-exposure. Sorry, the incidence in the exposed versus the incidence in the non-exposed. This is not this. This is trying to predict those that are positive using the screening test, those that are negative using the screening test. So then, other calculations that can be done is you can look at accuracy of a screening test, where it's determined by the following formula. It's A plus D divided by A plus B plus C plus D. So here, if you look at this, it's, as I said, it's A plus D. Sorry. So it's A, where the screening test is actually positive and measuring what it's supposed to, plus D, the screening test says negative, and also the gold standard says negative, all divided by the individuals that are within that particular analysis. Whereas prevalence, remember prevalence is, remember the number of cases of disease in your population of study. So this is A plus C, regardless of whether or not they're testing positive with the screening test. It's the prevalence of disease, all divided by A plus C plus, or A, B, C, and D. We will go through a number of these examples in class, and we'll do them in quizzes. But I want you to, these are the new calculations that you need to be comfortable with. So you need to be comfortable with calculating sensitivity, specificity, predictive value positive, predictive value negative, accuracy, and prevalence. And the reason why this is important is that this is what makers of screening tests, be it through behavioral type analyses or be it through biological type tests that are out there, that's what they're looking for at any given time. And for example, you can go and take like a pregnancy test. You know that there is a level of validity, a level of accuracy within these tests, and they basically give you tight windows within these types of tests. You have to follow these tight windows in order to maintain accuracy. You know of individuals that have taken a pregnancy test too early because they're anxious and they want to know, that comes out negative, but then when they take it within the window, they know through testing with the particular type of hormone that they're actually trying to detect, they know that they're more accurate at a specific level within that particular study or within these particular tests. Same way to look at this here with your glucose tests. For diabetes in that, there is a window, there 95% of the individuals shall fall within 15 milligrams per deciliter if they use the tool, the screening test, in the way that it's prescribed. And the way they do this is through regression analysis and other types of calculation to determine that accuracy or that validity. So there's lots of screening tests that are calculations that one could do. So for example here, where a screening test they're trying to determine how valid a particular screening test is on 500 individuals, and they're comparing it to the gold standard with these 500 individuals. So with this new screening test, they found that 200 individuals came up positive with the screening test that actually had the disease when they were compared to the gold standard, where there were 15 individuals that tested negative with this particular screening test, and when indeed they actually did have the disease. And then you can go moving forward and look at this, each of these numbers here. But you can see how sensitivity, this particular test, was 94.1% sensitive. It was 89.8 specific. It had a predictive value positive of 90%. It had a predictive value negative of 93%. 51% of the individuals within this particular study actually had the disease. And then the particular test was, the accuracy of this particular test was 92%. We're going, as I said, we're going to cover this over and over in the next couple of days, and so that you all are comfortable with this. I recognize it's another set of calculations that you need to be comfortable with, but this is what is so important for you to understand when it comes to what makes a good screening tool, and how accurate is it, how precise is this particular screening tool, and what things can come into play when we look at these different screening methods.